In this video, we'll finally look at the derivation for the pre-training procedure in a deep belief network. So now we've seen the variational bound, we're ready to see the detail of the derivation for how we can pre-train a deep belief network by first training in RBM, then taking its weights as the initialization of the first layer sigmoid belief net of a two hidden layer DBN, and then pre-train only the top RBM part. And then once that's finished, we use the weights of the DBN here as the initialization for the sigmoid belief net for the two hidden layers in a three hidden layer DBN, and then we train only the top RBM part, and so on for as many layers as we want. In what follows, I'm going to focus on the case where we start from a first one hidden layer DBN or just an RBM, and then we use it to initialize a two hidden layer DBN, where we take these weights, initialize the sigmoid belief net part here, and then train the top restricted Boltzmann machine here. So keep this specific case in mind in what follows. So we saw the variational bound, which gives us, for any model with some latent variables, a lower bound here on the actual log probability for some given observation x. And what we've seen in particular is that in this variational bound, we introduce a variational posterior q of h1 given x, and that if q of h1 is equal to p of h1, then it's actually very tight. We get inequality between this and that. And the closest actually q is going to be with respect to p, the posterior p of h1 given x, then the tighter the bound here is going to be. Okay, so that's something we're going to exploit in our derivation of the pre-training algorithm. All right. First thing we're going to do is that we'll, instead of writing this term here as log of p of x give p of x and h1, we'll write it as the sum of log of p of x given h1 plus log of p of h1. So that's because p of x given p of x and h1 is a product of this times that, and so if we take the log, it's just the sum of the logs. Okay. Now imagine that so in the single hidden layer DBN, which really is just an RBM, p of x given h1 and p of h1 depend on the same parameters of the same model. So this is just the regular conditional in the restricted Boltzmann machine, and p of h1 would actually correspond to p of h1 would be equal to the sum over all values of x of p of x and h1. So that's how we could compute p of h1 in one hidden layer DBN, or which is just a regular restricted Boltzmann machine. So when we jump to the two hidden layer DBN case, what we will do, as we've described before, is that to model p of h1, we'll use a separate model with its own set of parameters. And the model we'll use is going to be an RBM, which has its own additional hidden layer h2. So in other words, p of h1, once we go from a single RBM to a two hidden layer DBN, is going to correspond to the marginalization of that second hidden layer in this topmost RBM that we've introduced. So p of h1 is going to be the sum over h2 of p of h1 and h2, where this is an RBM with its own set of parameters that are not the same parameters as in p of x given h1. So this part is going to have its own set of connections between x and h1, and this is going to have its own connections between h1 and h2. So if we do this, it means that once we've added this second layer, we've now untied the parameters with respect to which we have to do an optimization where we're training between this part of the bound and this part. So now this part is free with respect to changes to this part here. because they have different parameters. And in the pre-training case, actually, we're just going to fix that part. We'll just assume that this is not moving anymore. We're using the same parameters for P of x given h1, and they're going to be set to the parameters of the single layer RBM that we've pre-trained initially. And so once we get to training the second layer, we only need to change, we're only changing this part here because the parameters aren't involved in that section. So if we train our second hidden layer to maximize the bound, it means that the only terms here that are dependent on the parameters of that second hidden layer are here. So in other words, we can ignore that because it doesn't depend on the second hidden layer parameters. And we can ignore all of this because Q of h1 given x, that's a separate posterior model, an approximate posterior, which we'll talk about in the next slide. But it's separate. It has its own set of parameters which are not adjusted. And so if we're maximizing this, then it's the same thing as minimizing minus that, which is here. So minus the sum over h1 of Q of h1 given x times log of P of h1. And because this is an RBM, it actually corresponds to minimizing the negative log likelihood of examples or samples from Q of h1 given x. So it's like we're training an RBM on data that was generated for by Q of h1 given x, by our approximate posterior. Okay, so when we're maximizing this variational bound, it's now been converted to the problem of training an RBM on some observations that are generated by this approximate posterior. So for a given training example x, what we could do is generate a bunch of samples from Q of h1 given x, and then use those, provide those to the learning algorithm of the RBM, which is going to optimize its parameters to minimize the negative log likelihood of these parameters. And if we have a whole training set of examples x, then it means that we would actually, for each training example, we would need to provide a set of samples from Q of h1 given x t. So now we'd have separate training examples. So we'd collect this big training set of sample hidden layers for where we get a few samples from each training example, and putting all those together, we'd feed that to the learning algorithm of a restricted Boltzmann machine, and that's how we could try to optimize this lower bound here. So this starts to look a lot like the pre-training procedure we've seen before, where to train the second layer of a feed-forward neural network, we'd transform all the data from its input representation x to the latent representation h of x, and then we train an additional second hidden layer on top of that representation. What has changed is that in this context, what is different is that we're actually sampling from a posterior to get these observations. We're not performing just a forward pass. Now, what should we use for this approximate posterior Q of h1 given x? This bound applies in any case, but we know that it's tight if Q of h1 given x is actually close to the posterior P of h1 given x in the two hidden layer DBM. So what we'll use is actually the posterior of the first layer RBM. So in other words, if you remember, if you have a single layer RBM, computing getting the posterior is equivalent to, or requires to do a feed-forward sigmoidal, computing a feed-forward sigmoidal layer, which gives us all the probabilities of each hidden unit. And then to sample from that posterior, we just look at each value of each hidden unit, and then this would give us the probability of each hidden unit being sampled to 1. So to get to sample from that choice of posterior, which would be the posterior of our model that has just one hidden layer and corresponds to an RBM, we would just compute a feed-forward pass and then sample. Now, what's interesting here is that if we initialize the weights of the second layer RBM in our two hidden layer deep belief network, then we will start our optimization problem at a point where this is exactly equal to that. And that's because a 2 hidden layer DBN is actually equivalent to 1 hidden layer RBM. So let's look at that in more detail. So imagine we have a 1 hidden layer RBM. So here, to simplify the illustration, just assume X and H1 are vectors. And now we want to actually initialize we want to start training a 2 hidden layer DBN, so where we have directed edges here, and we've added this second hidden layer here, and here we have undirected edges, so this forms an RBM. So the first thing to notice, if these connections are parameterized by W, and if we take then this same W and we fix it to the parameters here, and then for this layer we actually use W transpose. So in other words, we set the parameters here to be W transpose, the transpose of this matrix here, then this model and that model are exactly equivalent. So one way to think, to see this is that if we were to sample from this RBM, we would say initialize X to some random values and we'd perform Gibbs sampling. So we'd sample H1 and then X and then H1 and then X. We'd continue like this infinitely, and then at some point, you know, as if we get close to the equilibrium distribution, we could just observe X, and this would be a sample from the distribution. Now, if we wanted to sample from 2 hidden layer DBN, what we would do is that we could say we have to do Gibbs sampling here and eventually sample X. But because this is W transpose and this is W, performing Gibbs sampling here is equivalent to performing Gibbs sampling here. So in other words, when, for instance, we're sampling from H1 to X, this corresponds to taking H1 and sampling H2. It's the same, exact same procedure. And once we get an H1 and we sample X instead, then this actually, again, is exactly the same thing as taking H1 and sampling H2 instead. So in other words, if we take all of the Gibbs sampling steps here, they could equally have been derived by doing Gibbs sampling here, and then the very last step of Gibbs sampling going from H1 to X instead and observing X. So from that argument, these two models are exactly the same, which means that initially, if we've initialized the parameters of the second layer RBM as the transpose of the first hidden layer, then it means that the posterior, as we compute it in first hidden layer, 1 hidden layer RBM, is the true posterior also for that model. And so, if to sum up, if we initialize the 2 hidden layer DBM by first training an RBM, taking its weights W, and initializing the weights here to W and the weights here to W transpose, we have that by using this posterior Q of H1 given X, we are starting our optimization at a point where this is exactly equal to our lower bound here. And then as we're going to train in our greedy pre-training procedure only those weights here, so we're only changing the weights here, so they're going to depart from W transpose, then our approximation here, which is only going to use W, where W is kept fixed, as we're changing these values and we keep those fixed, then it's not going to be true anymore. Q of H1 given X is not going to be equal to the true posterior P of H1 given X in this 2 hidden layer DBN. But what's nice is that at least we have a good initialization starting point where we are tightly close to what's the true log probability of the data. And as we move along, well, we'll keep pushing from that point on the lower bound up, and which means that we're guaranteed to at least improve over a log of P of X a little bit. And as optimization progresses, then we'll all be optimizing a variational bound, so a lower bound of log of P of X, but at least we'll have started at a point where we're at the first step, we'll be guaranteed to improve it. And so that's a justification for providing, using this first hidden layer with its weights W to initialize the 2 hidden layer DBN. That's because in this variational bound setting, we actually get a tight correspondence between the variational bound of the 2 hidden layer DBN and its actual log probability for some given example x. Okay, so I've just described how we set Q of h1 given x. We just use the previously pre-trained weights to derive our posterior over the hidden layer h1, and then we'll use that posterior to train an RBM, which is the second layer RBM. It corresponds to P of h1 here. And the way we do that is that we take each training sample xt, we sample a hidden layer for it, we construct a training set like this, and then we feed it to a learning algorithm for a restricted Boltzmann machine, which is going to train the weights of that second hidden layer. In practice, people often, instead of sampling from Q of h1 given x, they will actually use the vector of probabilities as if we were doing forward propagation in a regular neural network. This is really an approximation. There's not a lot of justification for doing that, but that's what people do in practice. If most hidden units are either 0 and 1, it's going to be very close to the actual thing. And in practice, it works well. And now if we do this, then we get exactly the pre-training procedure for feed-forward neural network, where we use, because this vector of probabilities is this h of x that we've defined in the context of a feed-forward neural network. So then we get exactly the pre-training procedure. Now we can repeat this procedure by adding more and more hidden layers. So we started with a first hidden layer, one hidden layer RBM, and then we use these weights to initialize a two hidden layer RBM. And then again, what we do for a three hidden layer DBN, sorry, I meant a two hidden layer DBN here, and then to get a three hidden layer DBN, we just take the prior here and convert it into an RBM, and then we use the weights that were pre-trained here as the fixed value for these weights here. And then to get our posterior up to this layer here, we actually go up by using the same weights. Okay, so we're using the same weights to go up in the hidden layer. Now at this point, once we're at three hidden layers, we don't get a tight lower bound over log of P of x. So this argument that I said where we get an equivalence and a tight bound doesn't apply once we reach three hidden layers. But still, it does, the procedure still corresponds to maximizing a bound on the actual log likelihood of the data for that DBN. It's just we're not starting at a point where we actually are exactly equal to log of P of x. So in theory, as we go on, we're not guaranteed that our approximation, as we're training the DBN for the posterior Q of h1 given x or Q of h2 given x, once we're at training a third hidden layer, we're not guaranteed it's going to be close to the true posterior. It might actually get very far. So this only means that we're improving. We might not be improving on the true log likelihood. We're just going to be improving on the variational bound. But still, we might be extracting better features by doing this. And as we've seen, if we think of this procedure as a good initialization for a feed-forward neural network, we actually do get a good initialization, so a good set of initial features that are implemented by each hidden layer, and that after some supervised fine-tuning provide good results. Now, in the context of a deep belief network, we do have a specific fine-tuning algorithm for fine-tuning, in this case, the value of the sum over our training example of log of P of xt. This algorithm, known as the up-down algorithm, is described in the original reference for deep belief networks. I'm not going to talk about it here, but you can go look it up. It would be useful if we wanted to do train this deep belief network in a non-supervised way and train all hidden layers at the same time, as opposed to just adding layers one after another. And if we do this pre-training procedure first before doing the up-down algorithm, we get better results. And that's how this pre-training procedure was first proposed. All right, so for more details on deep belief networks, I really encourage you to look at this paper. In a sense, it's really the paper that started the whole deep learning recent advances in the literature. So it's a really good read. It's worth taking a look at. And that's about it for deep belief networks.